Yeah, you got It's a bar owl. He was, we were in the creek. So like I was in years and I was we were like going through the creek and he was sitting in the branch and we kept like falling branches nearby. And then eventually just like sat up there and watched us the entire time we were taking like a reflection. I think that it was his family and then it was he was coming. So like I got like right under him in the tree and he was like leaning down. Yeah.
I am going to let people pick this up at the end of class. If you are wanting to program your calculator with the quadratic equation, this is fairly straightforward. It doesn't take very long. You can pick up the instructions. This is for TI-83, TI-84. If you have a fancier calculator, we may have to look at it. But for most of the basic TI calculators, this program will work. So there is that. The next thing I wanted to do is I have the first draft of exam 2 written, because exam 2 is next Friday. I am going to go over what you can expect on exam 2. The very first question is about collision theory and catalysts. So it's a conceptual question. The second question is going to be related to reaction quotient, which we will go over today, and what reaction quotient tells you about the reaction. It also involves a Kc-Kp conversion. For the next set of questions, I give you 3 graphs, and it's the integrated rate law. So some of the questions would be, okay, what order is the reaction based off of the graphs? What would be the rate law if the reactant discussed in the graph is the only reactant? What would be the rate constant for that reaction? Then you use the integrated rate law to figure out either initial concentration, the ending concentration after a certain amount of time, or something along those lines. And there's a half reaction. The next question is about method of initial rates, where you have to determine the order of reactants, write a rate law, and determine the overall order of the reaction. The next question is about writing an equilibrium expression and understanding what the equilibrium constant means. And then understanding the relationship between the equilibrium constant and what the equilibrium constant would be if you reverse the reaction, if you multiply the reaction by some multiplicative, or if you add reactions together. So stuff we went over on Wednesday. The next question is a reaction mechanism question, where you have to determine the overall reaction. You have to answer questions such as the molecularity of the step. You have to determine what the rate law would be if it was an acceptable mechanism. You have to know, is there a catalyst? And if so, what it is. If there's an intermediate, and if so, what it is. You need to know the rate determining step. You need to understand how catalysts impact reactions. And then you need to be able to take a reaction mechanism and essentially compare that to a energy of activation diagram. and determine whether that energy of activation diagram would match a specific reaction mechanism or not. The last question is the only question we haven't gone over, and I don't expect to go over it until Monday, and that is Le Chatelier's principle. We will see whether Le Chatelier's principle is on this exam or not. You are given all the equation, you are given, again, I give you your equations, including all of your integrated rate laws and half-lives. Now, I've got the integrated rate laws and half-lives mixed up. They're not in 0, 1st, 2nd order. You're also given the K prime equations where you're calculating K prime based off of an equilibrium constant and changes you make to a reaction. And you're given your Kp, Kc conversion formula. The other thing you're given is you're still given your, not that I think you need it, but your solubility rules and a periodic table. So that is the test as of right now. The only question is, basically I've got to take the test to determine how much time it's going to take. Before I know whether this is the exact exam. The only thing it will do is get shorter. It will not get any longer. Any questions? There are several homeworks that are related to what's on the test. If you do them, you should be several optional homeworks related to what's on the test. And if you do them, you should be prepared for my exam. Questions? Last thing I need to make an announcement is for the service learning project. The list of materials, the cost, and where to find them is due to me by Monday. So whoever the treasurer is has a task that needs to be turned in by Monday. I've had one so far. And it's to be emailed to me, not in your Google Doc folder. It's to be emailed to me so that I can put a list together of what I actually need to purchase. Okay. So what we're going to do today is I'm going to do another problem where we determine the equilibrium constant by being able to use a series of data that is provided to us and ice tables. Then we're going to get into reaction quotient and work through the reaction quotient. Finally, if time permits, we're going to get into solving for X if all you know is your starting quantities and your equilibrium constant. Okay, so I have a reaction where 2A aqueous plus B aqueous goes to form C gas plus D gas. And I am told that the initial moles of A is 1.00 mole. The initial moles of B is 0.80 mole. The initial moles of C is 0.00 mole. And the initial moles of D is 0.00 mole. I am told that the volume that this reaction takes place in is a 2-liter container. And I am told that the final concentration of D is 0.20 molar. These are the pieces of information that I have been given. Okay, and I have been asked to calculate A, B, and C at equilibrium. And to calculate the equilibrium constant Kc. Okay. First of all, if I'm going to calculate Kc, Kc is going to be equal to the concentration of C times the concentration of D divided by the concentration of A squared times the concentration of B. Basically, all I've done is write the equilibrium expression. Note you need concentrations. Or in other words, we need the molarity of our solutions. We don't need moles. So I'm going to rewrite this equation and we're going to work from there. So 2A aqueous plus B aqueous goes to form C gas plus D gas. And we're going to develop an ice table or a rice table, whichever way you want to say it. But I need concentrations, folks. I don't need just moles. And in the original problem, I was given just moles. So the first thing you need to do is you need to convert all of your moles into concentration by taking those moles and dividing it by the volume in liters. So for our A, we have 0.50 molar A. For B, it's 0.40 molar. For C, it is still 0.00 molar. And for D, it's 0.00 molar. The change that occurs, according to this balanced reaction, we're going to lose 2x of our reactant A. We're going to lose x of reactant B. We're going to make x of reactant C, and we're going to make x of reactant D. Now, according to our So, according to our background, the final concentration of D was 0.20 molar. So if we think about this, for D, we know that 0.00 plus X has to equal 0.20 molar. Solving for X, that means our X is 0.20 molar. For concentration of C, it was 0.00 plus X, or in other words, it's 0.00 plus 0.2 molar. So it's 0.20 molar for C as well. For B, it was 0.40 molar minus X, so it's 0.40 molar minus 0.20 molar, or in other words, it's 0.20 molar. And for A, it was 0.50 minus X, minus 2X. So that's 0.50 minus 2 times 0.20, or in other words, it's 0.10 molar. Any questions about how I got the concentrations at equilibrium? Yes.
So is the final concentration of B is always going to be X in this scenario, or?
In this scenario, yes, because we had 0 plus X. So our X, we were told it was 0.2 molar.
Gotcha.
So X had to be 0.2 molar in order for that to work. The coefficient in front of the X in this one is because of the stoichiometry. Other questions? Okay, so we have figured out our concentrations of A, B, and C at equilibrium, but we were also asked to figure out the equilibrium constant. And again, that's going to be the concentration of C times the concentration of D, all over the concentration of A squared times the concentration of B, this coming directly from the chemical equation. So plugging in our values, K is equal to 0.20 times 0.20 divided by 0.10 squared times 0.20. So our Kc comes out to be equal to 20. Questions?
Two above, you put K, KC, like.
Yeah, I was solving, it asked for Kc. So, yeah, this is technically Kc. Other questions? Yes.
So the calculating A, B, and C at equilibrium was the part where we have smaller concentration.
So the first thing we did was, because, first of all, because we want Kc, that means we need concentration, because that's what brackets mean. Therefore, you had to get the concentration of each of your starting materials by dividing the moles by the liters. Now, they gave you the concentration of D in molarity to begin with. And so then we just work from there. Did that answer your question?
I was asking which step specifically was you referring to when you said ABC. Is that
Oh,
calculating?
this is this number.
Okay.
RICE stands for reaction, initial concentration, changing concentration, equilibrium concentration. Other questions? Yes.
Is your initial, can you just go one more time how on your initial concentration you went from like, how we got those 0.50 and 0.40 for A and B?
Because what is the most common unit of concentration we use? Molarity, which is moles per liter. So I took the moles that was given and divided it by the liters. And that was it. Other questions? Okay, if there are no other questions, then we're going to talk about the reaction quotient, which I introduced at the end of last class. The reaction quotient is calculated just like K. The difference is K means the reaction is at equilibrium. Where Q indicates whether the reaction is at equilibrium or not. So what we know is when we calculate Q, if Q is less than K, equilibrium has not been reached. And the reaction proceeds towards the products. If Q is equal to K, then equilibrium has been reached. And if Q is greater than K, that means that we are past equilibrium. And the reaction proceeds towards the reactants. Let's look at one of these in, let's look at one of these. So consider the reaction N2O4 gas goes to make 2 NO2 gas with a Kc of 5.85 times 10 to the negative 3. a reaction mixture contains NO2 of 0.0255 molar and N2O4 at 0.0331 molar. Calculate Q and determine determine the direction in which the reaction will proceed. Okay, again, Q is calculated identically to K. So Q for this reaction is going to be equal to NO2 squared divided by N2O4. So our Q is going to equal 0.0255 squared divided by 0.0331. And therefore we get a Q of whoops. You get a value of 0.0196 for your Q. Or in other words, we're looking at 1.96 times 10 to the minus 2. $1.96 times 10 to the minus 2 is greater than 5.85 times 10 to the minus 3. So therefore, Q is greater than Kc. So this reaction proceeds towards the reactants. Because Q is greater than K. Questions? Yes.
Say again, how we know which one is confirmation under.
When you write an equilibrium expression or Q, it is the products raised to their coefficient divided by the reactants raised to their coefficient. So it would be the NO2, since it was the product, raised to the power of 2, since that's its coefficient, divided by the reactant N2O4, raised to its coefficient of 1.
Thank you.
Folks, that's all there is to Q and K. The big thing about Q is Q means it's not at equilibrium necessarily. You have to determine whether it's at equilibrium. If it's not at equilibrium, it's going to proceed to equilibrium. It's going to move in a direction so as to reobtain equilibrium. But otherwise, calculating Q and calculating K are done the exact same way. It's just what they mean is different, slightly different. Questions? Okay. So up to this point, you have been mainly calculating K. That's been our entire goal up to this point, really, is to calculate K. Whether we manipulated the reaction and calculated K prime from the original K, whether we calculated between Kc and Kp, or whether we calculated K from the concentrations at equilibrium. Your main goal has been to figure out what K is equal to. And then finally, we talked about Q versus K. Now, what we're going to do is we're going to talk about finding equilibrium concentrations. But you're not going to be given an equilibrium concentration to find. So you're not going to be finding 3 out of 4. You're going to have to find them all. So how do we do that? We're going to be setting up our equilibrium expression. And then you're going to be using algebra that sometimes will involve using the quadratic equation to solve. Let me illustrate. N2 gas plus O2 gas goes to form 2NO gas. This has a Kc at 2000 degrees Celsius of 0.10. If you are initially given the concentrations of 0.200 for N2, 0.200 for O2, and none of your NO, I want to know the concentration of each species at equilibrium. To figure that out, we're going to set up a Rice table. We've got our reaction, we've got our initial concentrations. The next thing we need is our change in concentration. According to the balanced chemical equation, we lose 1 nitrogen during the reaction. According to the balanced chemical equation, we lose 1 oxygen during the reaction. And according to the balanced chemical equation, we make 2 nitrogen monoxides during the reaction. So at equilibrium, it's 0.200 minus X for our nitrogen concentration. It's 0.2000 minus X for our oxygen concentration. And it is plus 2X for the nitrogen monoxide concentration. Any questions so far? Now we're going to write our equilibrium expression. Our Kc is going to equal the nitrogen monoxide concentration squared divided by the nitrogen concentration times the oxygen concentration. One of the most common mistakes I see is that people don't take that extra second to write the Kc equation. And because they don't, they screw up what gets squared and what doesn't get squared. So now Kc is 0.10 is equal to our nitrogen monoxide concentration squared, so 2x squared, divided by our nitrogen concentration of 0.200 minus x times our oxygen concentration of 0.200 minus x. Starting to simplify this problem, 0.10 is equal to 2x squared is 4x squared. Divided by 0.2 times 0.2 is 0.0400 minus 0.200x minus 0.200x plus x squared. I know that they teach how to take a problem and convert it into this type of thing different than what I did when I was in school, which I used FOIL, which is first, outer, inner, last. I know there's other ways to do this, but that's what I just did, is I multiplied the first, I then multiplied the outer, I then multiplied the inner, and then I multiplied the last to get what's in the denominator. What's in the denominator well, this simplifies to 4x squared all over 0.0400 minus 0.400x plus x squared. You then multiply both sides through by the denominator, and you get 0.004 minus 0.04x plus 0.10x squared. And that is equal to 4x squared. We rearrange to set this equation equal to 0. So 0 is equal to 3.9x squared plus 0.04x minus 0.004. This is a polynomial that would use the quadratic equation to solve. The quadratic equation is x is equal to minus b squared plus or minus square root of 4ac all over 2a, I think. No.
Or B not squared.
Minus b plus or minus the square root of b squared minus 4ac. Sorry, it's been a while. I cheat in that I use my quadratic equation in my calculator. All over 2a.
There's a song that helps me remember it.
Now you can do this the hard way, or you can get your calculator set up. I suggest getting your calculator set up, which I haven't done. I set up somebody else's calculator yesterday. So what did you get your x values as?
It's -1.
-1?
-1 plus 25. It's plus 25 squared is 0.6256 divided by 1.
Something's up.
I've done my quad right now.
Okay. Can I borrow your calculator? I set yours up yesterday. Yes, you did. So let me put these in here real quick. So when you key this in, you should have gotten two possible x values. One is 0.415, and the other one is a negative 0.5713. My other calculator is the one that has the quad. Now, only one is going to be valid. When you get this, only one is going to be valid. So how do you know who's valid? Well, we go back up here. And we get our N2. Well, N2 was equal to 0.200 minus x. We had our O2, which was equal to 0.200 minus x. And we had our NO2, I'm sorry, our NO. Knew there was something wrong with that statement, which was 0 plus 2x. Yes.
Should that A value not be positive or negative? You're subtracting 4.0 x squared.
I swapped it. So I went to the right-hand side. If you would go the other way, yes, you'd get a negative x squared, a positive, or a negative x and a positive c. So it basically, I went to the other side, so I'd get a positive x squared. Now, here's how you know who is valid. If I have 0.200 and I subtract out 0.4153, That gives me a negative 0.2153. Concentrations cannot be negative. So that means that this first one is going to be invalid. Concentrations cannot be negative. The closest you can get to a negative concentration is 0, folks, because you either have some concentration or you don't have any concentration. And so you should be able to key in these. And one of these will come out to be a positive for all the concentrations. Something's off. How do I know something's off?
I don't know, I just have a question.
Yes.
So how come you took the 0.10 and put it to the x squared if it wasn't originally x squared? Like, how did you add it to the 1x?
Hold on. The 0.1x squared?
Yeah, how did you get the x squared on it? Because on the, whatever it's on the other side of the equal, there's no x squared. So I don't know how you.
Because I multiplied the denominator through by this number.
Oh. Okay,
So that would be 0.0400 times 0.1 minus 0.400 times 0.1 plus x squared times 0.1. And that's equal to 4x squared. I'm gonna have to correct this problem on Monday because there's something wrong with it. Why is there something wrong? Huh? You got the right answer, but there's still something wrong.
Subtract the negative and ones that add negative.
If I did this correctly, this would wind up with a negative answer. And you can't have a negative concentration ever.
So you have negative.
So I have a mistake somewhere. But I will say this, I know my mistake is in the quadratic equation. I've got to program the quadratic equation where I slow down. But that's how you work it. We'll do another one of these first thing on that. Well, I'll correct this. And then we'll do another one of these on the first thing on Monday. And then we'll do the Chaltier's principle Monday. Okay, you got the correct value. So there's something wrong with this quadratic.
That's all I was like.
Yeah. That's correct. That 0.02 should be the correct one. Make sure you program the quad. It'll save your life. And I gotta program the quad. So it saves my life.